So let's begin our second session of the afternoon and welcome Federico Poloni to talk about tame inverse Laplace transform of tame function.
Okay, thank you. And well, as you know, this is joint work with Nikita Denishkin, who's a PhD student at Scuola Normale. And I changed the title a little bit because we wanted to go with a nice acronym. And so, as some of you know, I'm coming from the numerical field, so I do numerical linear algebra. So I'm mostly interested in numerical computing and approximation issues. And I started this because we wanted to understand a little more about the numerics of Abate-Witt methods for inverse Laplace transforms. So inverse Laplace transforms are a tricky numerical problem, unlike Fourier transforms, because essentially because it's simple. So you can have functions that have very close transform, but if you go back to the original function, then they're very far apart. And so there have been many different methods in the literature. So this book is on numerical methods, and I can only tell you that it has a chapter that makes a survey of existing surveys on the problem. And in most cases, the interest is in functions that have kinks, like this one having a jump. I took this picture from the website of Miklos, Telek, and co-authors who suggested recently a new method for that. And but I would say here in queuing theory, in many cases, we're interested in functions that we know do not have kinks, like jumps or jumps in the derivative. For instance, we're interested in phase type distributions or in the first return matrix from fluid queues that Magojata already spoke about. And those are very regular functions. They're C-infinite functions. So a natural question is, can we do something better if we assume that our function has a very special form? And the answer is yes, it turns out a little better. And so let's focus and restrict the field. First, we restrict to very special functions. We will see soon what they mean, mostly sum of exponentials or something similar. And we're also restricting our methods to Abate-Witt methods that are essentially, you can take t equals 1 in this formula and assume essentially you want to reconstruct your function as a weighted sum of evaluations of the transform. So you're free to evaluate your function in a certain set of points beta. Oops, sorry, these indices should have been n's, not i's, small n instead of I. And then you want to reconstruct it with as few points as possible. And there are many methods in this framework that differ mainly for the position. Sorry, for the position of the poles beta I, beta n. And what about the numerics? So there is this table with a quick recipe in Abate-Witt, but they're mostly interested in computing in high variable precision, so more than normal floating point precision. And essentially they tell you how many digits of precision you should use, how many points you should use to get prescribed the number of correct digits in the functions. And for instance, if you're using the Talbot method, if you have 16 digits, then you should always use 16 poles, 16 evaluation of your functions. That's fine, but that looks like a bit of a general rule, right? It seems strange that with 16 points we can reconstruct all the functions in the world. So we think there must be something more here. And so our goal is figuring out the numerics, figuring out what matters for this approximation, and hopefully hopefully get some new methods out of this understanding. So in addition to the classical methods in the Abate-Witt framework, there's a more recent method by Matrix-Analytic and his co-authors, Horvath, Almusa, and Taligas. And essentially their idea is they wanted to approximate a delta function, so a delta, so with a very high peak. Sorry, this thing doesn't seem to work great. Okay. With a very high peak, they want to approximate it with a weighted sum of exponentials. And this leads to a clear approximation method. So you approximate your delta with a weighted sum of exponentials, then you immediately get an expression that is equivalent to an Abate-Witt method. And the next thing we would like to speak about is how we can change this approximation. So from delta distribution in 1, we replaced it with weighted sum of exponentials. And we want to do something slightly different instead. We want to take the Laplace transform of that relation. This is something that has been done already in the 70s by Zakian, who worked on this methods. And essentially, if you take the Laplace transform of this relation, then you get that you want to approximate the exponential of minus y with something that is essentially a rational function, so a ratio of fractions if you put it on a common denominator. And this is a very old problem in interpolation theory. This is what they call rational approximation. Essentially, you have a function, and you want to construct a rational function that approximates its well, so a ratio of polynomials. And one of the classical methods is so-called Padé approximants, which are a sort of moment matching. So essentially, you want to make sure that this rational function has a Taylor, has a Taylor expansion that coincides with the Taylor expansion of the function that you want to approximate, and this boils down to certain relationships among the coefficients of P and Q. And let me note also that it's not immediate why it's a good idea to take the Laplace transform of this relation, because if you have a small error in the z domain on this approximation, it doesn't immediately map into a small error in the y domain into this approximation once you take the Laplace transform. But it turns out if your function has a very special form, then there is a very natural explanation of why this works. So let's introduce a definition. So we say that an Abate-Witt method, so a way to choose the beta n's and the wn, is epsilon accurate on a certain domain omega if the error in this approximation of e to the minus y with a rational function is bounded uniformly by epsilon for all y's in the domain. And we can see that this produces a direct explanation of why the Abate-Witt method works, because so this is an exponential function, and this is essentially the Abate-Witt approximation of the exponential obtained, because these are essentially the Laplace transform. This is Wn times the f hat of beta n. So long story short, so once you have that definition in place, it's not that complicated to prove this theorem that if your function is itself a weighted sum of exponentials, then the Abate-Witt method is accurate on this function. With so this epsilon is the error, approximation error from above, and you get the sum of the coefficients. And for this, you have to assume that your Abate-Witt method is accurate on all the alpha I times t. So that's the interesting first message, that every method is can be accurate only on a certain region omega of the complex plane, and your exponential rates times t have to be in that region of the complex plane for the error to be small. And so the omega you need depends on the exponents that you have. If you have a function with certain exponential rates, then you need an Abate-Width method that is accurate on the corresponding region omega. And if you plot the approximation error, so this is a plot in the complex plane in the y domain of this error here, of this error here in the y domain, then you can figure out where the methods are most accurate. So this is an example. This is the Euler method with 37 points, and it tells you that this method is going to do very bad in points that are on the imaginary axis very far away from the origin. So this is where the e to the minus y is essentially a sine or a cosine and oscillates a lot. And for another example, this is one of the methods that we'll be constructing. This is a method that we have constructed to be accurate on a circle centered in 1 with radius 1. So it's accurate here, but if you test it then on a larger circle, then it stops being accurate. So if your goal is constructing something that is good in this region here, then it's not going to be it's not going to be accurate in another region. Okay. So that's the main idea. This works for scalar sums of exponentials. What if we have a matrix exponential, so something like a phase-type distribution? Well, you could in principle take a Jordan form, but the problem with this Jordan form is that you don't have control over the coefficients Cm, right? Because if you take a Jordan form, then this V could be arbitrarily ill-conditioned, so you could have very large coefficients. There's, however, a technical tool, so a newer trick in the numerical literature that lets you find uniform bounds at the expense of making your region of accuracy a little bit larger. That's the one. So we introduced this definition. This is called the field of values of a matrix. And it's essentially the set of all possible Rayleigh quotients that you can get out of this matrix. U star AU divided by U star U, where U is any vector. So for a given matrix A, this WA is the region that you can get with all these ratios. It always includes the eigenvalues. So this is an example of a 5x5 generator matrix. The eigenvalues are in red, and this region W of A is in light blue. And as you can see, this region extends a little bit farther away from the eigenvalues. So it's a little bit more. And depending on the matrix, this region can be larger than the convex hull of the eigenvalues, let's say. The convex hull of the eigenvalues is always included because this is a convex region, but it could be larger. For instance, if you have a Jordan block, the eigenvalues is just 1, but this region is a large circle. What do we need this definition for? We need it for a theorem that tells you essentially that if a function, any holomorphic function is small on the field of values of a matrix, then it's also small in the 2 norm on the matrix. So this tells you that if you have a rational approximation of the exponential that is good on scalars inside W of A, then it's also good on the matrix itself with just extra coefficient 1 plus square root of 2. Actually, this 1 plus square root of 2 is, it's conjecture that it can be even lowered to 2. So there are no known examples in the literature where this is larger than 2 instead of the 2.4 that this has actually been proved with. So with this technical tool, we can prove that if we have a matrix exponential and we try to reconstruct it from its Laplace transform, the Laplace transform of this matrix exponential, Laplace transform of this matrix exponential is the inverse, the resolvent, so Q plus beta identity. And if you sum a few of this, then you can get something to reconstruct the exponential. And then you get this error. So as you can see, we're very close to being able to say something about phase type distributions, and this will be in our next slides. What does this imply for phase type distribution? Phase type distribution is the time to absorption of an absorbing continuous type Markov chain. We've already seen it here. Here's the notation. I'm using alpha transpose as a vector, and I'm using Q, big Q and small q, because we already need t for the time. And let's say you have phase type distribution. Then for this, if you have a Butterworth method that is accurate on a region that includes the field of values of minus tq, then you have this bound on the error. So your approximation error epsilon becomes 1 plus square root of 2 times epsilon times a certain quantity that is, well, if you want to approximate the PDF, sorry, the density function, then you have an error that is proportional to q, small q. And if you want to approximate the CDF, the cumulative distribution function, then you have an error that is proportional to the first moment times the approximation error in your Butterworth method. But of course, the tricky part here is estimating the field of values of this matrix, which we said is something larger than the spectrum itself. How can we do that? Well, there are some general results. First of all, you can compute the field. You can compute an approximation of the field of values of a matrix and inclusion just by a couple eigenvalue computations. We don't see exactly why. And there are also general inclusion results on field of values. For instance, this I said was a 5x5 generator, and one can prove that every 5x5 generator has a field of value that is included in this rectangular region. So as long as our rational approximation of the exponential is accurate in this rectangular region, then it's going to work well for all 5x5 generators, for all 5x5 phase type distributions. So generators and sub-generators, which is what we need for phase type distributions. And that's fine. The only problem is that the dimension of this region essentially grows according to the square root of the dimension. So if you have a large matrix, then you have to construct a method that is approximate on a very large region. So in many cases, it's better to try to compute a region that is optimal for your matrix. In this case, you can compute an inclusion that is tight, or you can compute the optimal rectangle that includes this this region in with just two eigenvalue computations. So you can either have a general method that works on all matrices, but you need to be accurate on a large region, and so you're going to need more poles, or you can tailor a method especially for your for the matrix that you're working with. And so this was for phase type distributions, but now we come to the problem that we started with, that we wanted to say something about, and it's the psi matrix in fluid cubes. This is because there's a paper from 2008 by Bean, Magojata O'Reilly, and Peter Taylor that gives us a way to compute the Laplace transform of the matrix psi with a direct algorithm. So it's simpler to compute the Laplace transform of this function than to compute the function itself. By the way, for a definition, we have a fluid model. So a model in which you have a level that grows with a derivative that depends on the state of a continuous time Markov chain. And essentially, this psi is a function that measures the length of a busy period in the queue. So we start from level 0. We want to end up in level 0, and we want the probability of returning to level 0 in a time smaller than t, and this is psi of t. So we define two of them. We define big psi, that is a sort of CDF, cumulant function, and we define small psi, that is the corresponding density, so it's derivative. And we're interested in telling how to reconstruct these both from the Laplace transform. And the key to do this is, well, at least theoretically, it's a closed formula that was that follows from some work that again Barbosa, Ricola, and Telek again did in 2001. We worked on MAM10. We presented in MAM10 some more specific algorithm and probabilistic interpretation for this method. Essentially, you can write small psi as a certain the sum of a certain series that depends on certain matrices bk that depend on that are essentially first return probabilities depending on the uniformization of your fluid model. And here lambda is a uniformization rate for the fluid model, so a scalar that is bigger than all the elements on the diagonal of Q. And this is the formula, but the nice thing is that you can rearrange it to essentially become a phase type distribution. So if you truncate the series, if you stop not at infinite but a certain big K, then this is a phase type distribution with this matrix Q that is K times K. And that is going to be the main trick. Since we know how to deal with phase type distributions, then our psi is the limit of phase type distributions, and they're phase type distributions with a very special Q. So since this Q is very special, we don't have to do any work to estimate its field of values. So the field of value of a Jordan block is known in closed form, and it's essentially a circle. So the theorem that we can get is that if you have an abiter width method that is accurate on a certain ball that is centered in T lambda and of radius T lambda, where lambda is any uniformization rate for your fluid model, then you can get these two bounds. So essentially the bound of big psi is the approximation error that you had, epsilon times lambda, uniformization rate, times the first moment of your distribution psi of t. So we can get a specific quantitative error bound on your method that depends on how good is your rational approximation of the exponential on a ball of center T lambda and radius T lambda again, so tangent to the origin. And so now the next question is, how do we construct a rational approximation of the exponential that is good on a region like this? And there's a trick in the numerical literature. There's a newer algorithm that was invented in 2018, so pretty recent. And basically, I'm not gonna give the details, but basically the idea is that you work with a special representation of your rational function in this specific form, where u, uk, fk, and zk are parameters. And here you see some z minus zk in the denominator, but if you cancel out the denominators, these these are not real poles. So the z minus zk, the denominators cancel out if you multiply numerator and denominator here by a common factor. And in fact, this rational function in this form essentially interpolates on zk. This rational function takes the value zk and fk. So take the values r of zk equals fk. And then you have to choose parameters uk as well. You can do it by essentially solving a least square approximation problem, a linear least squares problem, so very, very easy to do, just some linear algebra. And then the trick to construct good rational approximations is doing something greedy. So we start, you have a set of points on which you want your approximation to be accurate. If you want your approximation to be accurate on this disk, you take a few simple points on the circle. You assume that you interpolate exactly on a small set of these points. Let's say you want to assume that it's accurate only on this single point. Then you compute the error on all the other points. And if it's too large, then you add one more interpolation point and continue. And it turns out you just need a very small number of interpolation points to get accuracy, to get very low accuracy. For instance, if you want this to be accurate to a circle of radius 1, it turns out essentially 7 points are enough to get you up to machine precision, essentially. And the fact that we can only take points on the border is because of complex analysis. So there's a maximum model room principle that tells you that the error is larger on the boundary. So yeah, if you do this, then you can compare the accuracy of this method with other existing methods in literature. So you can see that many of these methods have a phenomenon for which they can get down to a certain specified accuracy, and then they start diverging, and this is where numerical issues show up. The point is that to get good approximation in infinite precision, you need large weights wk. But then if you compute this in finite precision, then you get numerical cancellation because you have large weights that cancel out because they have different signs, and so you have a maximum limiting accuracy for many methods. For instance, for the Gaver method, you get more or less you need more or less 16 points to get to machine precision 10 to the minus 16, and this is the rules of thumb that we're in a battle with. And it turns out that the method by Zakian was very good for the approximation, and that this method that we dubbed TAME, T-A-M-E, because we do AAA, you use the AAA method. AAA method is this new method for rational approximation, and we do the AAA method for the metric exponential. And so with this, we can basically get machine precision accuracy with just a very limited number of points. Here we just need 4 points, actually 4 plus their conjugates. As in many Abate-Witt method, you can use the fact that the poles are complex conjugate to just divide by 2 the number of evaluation. But essentially with 4 evaluations, we get to machine precision, and this is better than many other methods. And it's also interesting to note that this CME method that was very good for functions with kinks, for instance, jumps or jumps in the derivative, is instead not great for these very regular functions. But here it works because our functions are very, very tame. So we can use just rational approximation here. This is another more difficult problem, which we took a larger lambda t. So we need approximation on a larger region of the complex plane. And here our accuracy starts to suffer a little more. And surprisingly, I'm not sure exactly why this happens, but the Talbot method uses a lot more weights, sorry, a lot more poles and evaluation points, but it can get higher accuracy here. This we still haven't figured out exactly why. And so that was more or less it. We think we figure out what the important factors are for Laplace transforms of these very regular functions, and we suggested a new method based on the newer numerical literature.